Math 2414, representing functions as power series, video 10. Seventh example and final video in this series, integrating the unintegrable. Earlier in this chapter, and dare I say even earlier in this course, I was hinting that there are things that you cannot integrate in a finite number of steps. I'm pretty sure 1 over 1 plus x to the 7th is one of them, but I haven't checked. But regardless, I know that there are things that are unintegrable in a finite number of steps. What I meant by that was, if we can't calculate the antiderivative, maybe we can come up with an infinitely long polynomial that approximates the antiderivative. In other words, a power series. Let's integrate 1 over 1 plus x to the 7th dx by integrating its power series. Now, we could figure out the power series separate. In fact, let's go ahead and do that. No need to drag the integral sign along. This has a very strong resemblance to the sum of a geometric series. We just got to change the plus to a minus minus. And make note that a is equal to 1 and r is equal to negative x to the 7th. And so we need the absolute value of negative x to the 7th is less than 1. This will imply negative 1 is less than x is less than 1. Anytime a power of x is less than 1, then you're between negative 1 and 1. It's a good thing to know. So we can write this as the sum of n equals 0 to infinity of the first term, which is 1, which I don't need, times the ratio to the nth power. Let's go ahead and split this into negative 1 to the nth power times x to the 7n, because I'm going to integrate that, and it's easier to integrate if there's not a negative on the x. It's not impossible, you just have to do a substitution. Really like to avoid that. So the integral that we're looking for is going to be the integral of the sum of n equals 0 to infinity of negative 1 to the n, x to the 7nth power, dx. This is easy to integrate. We will pick up a constant of integration. Let's go ahead and write that. Sum n equals 0 to infinity. All right, to integrate this power of x, that's a constant in front relative to x, so leave it alone, the negative 1 to the nth. We're going to add 1 to the power to get 7n plus 1. Then we divide by the new power. And we know that we have convergence here. So just like that, we have a power series representation for the integral of 1 over 1 plus x to the 7th. Can we find the plus c? Not really. Because in order to find the plus c, you have to have a closed form version. Come on. A closed form version of the function, not an infinitely long polynomial. Like when we did arctangent, we could evaluate that at x equals 0. We don't have a function over here to evaluate to find c. So when you integrate a function by integrating its power series, unless you have more information, you cannot locate the plus c, just like doing any other indefinite integral. However, we do need to check for convergence at the endpoints. So let's move this series over here. N equals 0 to infinity, negative 1 to the n over 7n plus 1, x to the 7n plus 1. And we want to check at x equals 1 and x equals negative 1. X equals 1 is pretty easy. We have the sum n equals 0 to infinity of negative 1 to the n over 7n plus 1 times 1 to the 7n plus 1, but 1 to any power is 1, so that doesn't matter. I'll leave it to you to fill in the details, but this converges by the alternating series test. Okay? When we put in negative 1, we get the sum of n equals 0 to infinity of negative 1 to the n over 7n plus 1 times negative 1 to the 7n plus 1. And here we have that stealthy alternator situation where we see what looks like an alternator with an exponent, but it may or may not be an alternator. Really, the trick to saying you look like an alternator, but you're not one, is to ask yourself if the exponent is always even, or if the exponent is always odd, or if it fluctuates between the two. And if it's not immediately clear, like 7n plus 1, is that always odd? Is that always even? Looks like it's always odd, but put in n equals 1 and you'll see that it's even. But one way to see if an alternator is really an alternator is to just start sticking in values for n and seeing what exponents you get. For example, when I put in n equals 0 right here, I get 0 plus 1, which is 1. When I put in n equals 1, I get 7 plus 1, which is 8. And right away, I know it's an alternator because the powers switch between being odd and even. But just check it. If I put in the next value of n equals 2, 7 times 2 plus 1 is 15. If I put in n equals 3, 7 times 3 is 21, plus 1 is 22. So my exponents are alternating between being odd and even, which means -1 to that power is alternating between -1 and 1. So it truly is an alternator. But here's another situation. I've got an alternator and another alternator, which clearly is. When you multiply two alternators, is it always another alternator? Well, let's just put it this way. And I should have done this in a previous example. If you have two things that look like alternators being multiplied, you should merge them into one to see what it looks like by adding their exponents. If I add n and 7n plus 1, I get 8n plus 1. Is that always odd or even? It's always odd. How do you know? Well, anytime you multiply an even number, you get an even answer. In other words, an even times any integer is always even. You can't say the same thing for odd. Like 3 times 2 is not odd. But 2 times anything is always even. 6 times anything is always even. 8 times anything is always even. This guy is even. But if you add an even plus an odd number, it always ends up being odd. Think about it. So that 8n is even, which means that 8n plus 1 is odd. It's really not that hard to recognize odd or even numbers generically. You just have to practice, and then it's like, oh, that's an odd power. But since that is always odd, that means -1 to the 8n plus 1 is always equal to -1. So the numerator is not an oscillator, it is just a -1. Let's factor it out. This is a negative harmonic series, meaning that if I don't look at the negative, it's a harmonic series and it diverges. It's harmonic. Remember, you can spot a harmonic series when the denominator is linear. In other words, when the denominator looks like something that's in slope-intercept form and the numerator is constant. So we get convergence at 1, we get divergence at -1, and therefore our integral of 1 over 1 plus x plus 7 dx is equal to c plus the sum n equals 0 to infinity, -1 to the n over 7n plus 1 times x to the 7n plus 1 on the interval parentheses -1, comma 1 bracket, because we did pick up convergence at x equals 1. Okay, that's it. That's the end of this section.